The B-2 Spirit bomber is widely considered the most advanced stealth bomber ever built. While headlines focus on its ability to strike targets anywhere on Earth, every mission depends on an enormous amount of preparation. Thousands of maintenance steps must be performed perfectly, because a single mistake could turn this $2 billion aircraft into the world's most expensive lawn dart. The process begins inside the 509th Munition Squadron's assembly facility, where airmen prepare the weapons that will be carried inside the bomber's internal bays. The building is strictly climate-controlled because the bomb's guidance sections cannot tolerate dust or humidity. The temperature stays fixed at 68 degrees Fahrenheit, not for comfort, but for the ring laser gyros inside the guidance kits, which drift if temperatures change even slightly. The first step is attaching the MAU-169 guidance section to the front of the weapon. Inside this kit is a GPS antenna about the size of a hockey puck, and beneath it, an inertial measurement unit with accelerometers, capable of sensing movement smaller than a human hair. The control module receives targeting data from the aircraft and converts it into commands for the fins. A critical component is the umbilical connector, which lets the B-2 communicate with the bomb while it remains inside the aircraft. If this link fails, the weapon becomes an extremely expensive paperweight. Technicians tighten the guidance section with torque wrenches. Too loose allows vibration failure, while too tight can crack the housing. Next, they attach the tail kit that holds the fins and actuators. These fins are not simple metal flaps. Each one is driven by electric motors, able to adjust position in increments of 1/10 of a degree. Before any JDAM leaves the building, technicians run the actuators through programmed movements to ensure nothing binds. A fin sticking for even half a second could cause the bomb to miss by about 100 feet. The completed weapon is then weighed, because the B-2's mission computer requires precise values for ballistic calculations. Even a 5-pound difference affects timing. Throughout the process, one rule never changes. The JDAM must remain completely safe. The fuse stays unpowered. The guidance kit remains in test mode, and detonation is impossible. The thermal battery that powers the fuse activates only after experiencing the massive G-forces of being ejected from an aircraft. Until the B-2 releases it, the device is essentially a sophisticated lawn dart. After inspection, each JDAM is recorded in the weapon's database and placed on specialized transport trailers. These trailers maintain the same climate conditions as the facility, because even a short winter trip across the tarmac could affect the laser gyros. However, the weapons are not loaded until the bomber itself is proven ready. Preparing a B-2 becomes almost obsessive because the aircraft must be electromagnetically perfect, not just mechanically sound. On the flight line, maintainers from the 393rd Bomb Squadron confront the realities of physics. The B-2's stealth capability relies on precise control of electromagnetic energy, which requires a flawless surface. Before fuel, weapons, or engine start are considered, low observable technicians inspect the aircraft. The B-2's skin isn't painted like a normal plane. It is coated with radar-absorbent material containing tiny iron spheres that vibrate when struck by radar waves, converting energy into heat. Unfortunately, the material is fragile. Bird strikes, hail, or heavy rain can damage it, and any damage increases radar reflection. Technicians inspect every inch of the aircraft, searching for chips, scratches, bubbles, or rough areas. The leading edges receive special focus because radar waves strike there first. Engine inlets are equally critical, since flaws can create radar scatterers that reveal the aircraft's location. Panel seams are checked carefully. They are sealed with conductive tape that must remain perfectly smooth. Even a gap the width of a credit card can increase the radar signature enough for enemy radar to detect the aircraft. When defects are found, repairs begin immediately. Technicians sand the damaged area with precision tools. Sanding too aggressively creates reflections, while being too gentle prevents proper bonding. They mix specialized radar-absorbent compounds that remain workable for only minutes. Applied incorrectly, the repair could reflect radar rather than absorb it. The compound must also cure at exact temperatures. Too hot and it bubbles. Too cold and it will not bond. After curing, the surface is sanded flush to tolerances measured in thousandths of an inch. Across a foot-long section, the variation cannot exceed the thickness of a few sheets of paper. Maintaining a B-2 isn't simply fixing an aircraft, it's sculpting one. While stealth technicians work, other maintainers inspect mechanical systems. The B-2's hydraulics operate at pressures strong enough to cut steel. 4 independent systems provide redundancy. Losing one is manageable. Losing 2 is still flyable. But losing 3 makes landing extremely stressful. Flight control actuators are checked for sluggishness because every control surface matters on a tailless aircraft. Landing gear, brakes, tires, electrical systems, and environmental controls are also inspected. If anything fails, weapons loading stops immediately. The aircraft must be perfect before a bomb approaches it. Once inspections are complete, weapons crews roll the JDAMs beneath the bomber. Each bomb sits on a hydraulic lift that raises it into the weapons bay. Unlike other bombers, the B-2 carries nothing externally. All weapons must be stored inside to preserve stealth. The weapons bay doors are enormous, each weighing roughly as much as an SUV, and mounted on perfectly aligned hinges to avoid radar reflections. Inside the bay sits a rotary launcher resembling a revolver cylinder enlarged for bombs. It holds 8 positions, each capable of carrying a 2,000-pound weapon. The assembly can rotate a full 360 degrees in under 3 seconds, spinning nearly 8 tons of explosives. Weapons attached to suspension hooks rated at 14,000 pounds each. This may seem excessive for a 2,000-pound bomb, but combat maneuvers multiply weight. In a 2G turn, that bomb effectively weighs 4,000 pounds, and turbulence adds even more stress. Precise alignment is essential. If the interface is off by even the width of a penny, the weapon will not receive power or data. Load crews secure the lugs containing cables that allow the JDAM to communicate with the aircraft's stores management system. Without this link, the bomb would fall like a simple gravity weapon, potentially missing by miles. Yet the target coordinates are not loaded on the ground. The bomb does not know where it is going. That information remains in the aircraft's mission computer until seconds before release. This design not only protects security, but also allows targets to change during flight as battlefield conditions evolve. Even when fully loaded, the weapons remain inert, with unpowered fuses and sleeping guidance systems. Only basic communication and diagnostics function. The philosophy is simple. Keep the weapon as dumb as possible until the last moment. While the aircraft is prepared, specialists at the 509th Operational Support Squadron's Aircrew Flight Equipment Shop ready the pilot's gear. The B-2 flies so high that sudden depressurization would be fatal without immediate oxygen. Although its altitude ceiling is classified, it requires pilots to wear pressure suits rather than simple oxygen masks. Specialists test the masks on pressure rigs simulating high-altitude breathing, ensuring oxygen delivery even under G-forces. Microphones are also tested, because communication must work perfectly in emergencies. The pilot helmet alone costs more than many homes. Besides protection, it includes heads-up display compatibility, night vision capability, and flash protection capable of shielding the blinding light of a nuclear detonation. The visor can turn from clear to opaque in milliseconds. Technicians inspect survival vests containing emergency beacons, signal mirrors, and water purification tablets, equipment intended for the possibility of ejecting over hostile territory. Anti-G suits are also checked carefully, because their inflatable bladders must maintain exact pressure levels. Too little pressure leads to blackout during maneuvers, while too much restricts breathing. Each suit is custom-fitted, which matters because B-2 missions can last up to 40 hours with aerial refueling. After these checks, crews perform one of the most hazardous procedures in the U.S. Air Force: hot pit refueling. Normally, aircraft are refueled with engines off, but during this operation, the engines remain running. The B-2's 4 engines idle while producing enough heat to melt aluminum. This technique is used when rapid turnaround is required. Fuel crews approach wearing silver proximity suits, resembling astronaut gear, designed to tolerate brief exposure to intense heat. They carry fire bottles capable of projecting foam up to 30 feet. The first step is grounding the aircraft. During flight, it builds up static electricity, thousands of volts seeking a path to ground. One spark near fuel vapors could cause a catastrophic explosion. A thick grounding cable attaches to a bare metal point on the landing gear. High-flow hoses then connect to the single-point refueling port, pumping fuel at about 600 gallons per minute. In less than 30 minutes, the aircraft can receive roughly 167,000 pounds of JP-8 fuel. But distribution matters as much as quantity. Too much weight forward makes the aircraft nose-heavy, while too much aft causes instability. Because the flying wing design lacks a tail, balance is critical. Fuel temperature must also remain within limits to prevent poor flow or vapor bubbles that could cause engine flameout. Right before we continue, if you're enjoying this level of details and want more breakdowns like this, hit that subscribe button now, because your support means a lot for us. When refueling finishes, the B-2 is armed, fueled, and stealth certified. Pilots enter through a hatch behind the nose gear and climb into the cockpit, strapping into ejection seats that are essentially survival systems capable of launching the crew clear of the aircraft in less than a second. The cockpit is a digital glass panel filled with displays and keyboards. The mission computer alone has more processing power than the entire Apollo program once used. Startup requires a precise sequence. The inertial navigation units begin an 8-minute alignment while the aircraft must remain perfectly still, allowing ring laser gyros to measure Earth's rotation. Military encrypted GPS loads next. During taxi, the pilots check control surfaces. Because the B-2 has no vertical tail, yaw is controlled by split drag rudders at the wingtips that open like air brakes. Elevons move through their full range for pitch and roll. Even taxiing requires planning because the nose wheel sits 110 feet ahead of the main gear. Before takeoff, the crew reviews rotation speed, abort procedures, and emergency actions. At maximum weight, the B-2 uses most of the runway. When the throttles advance, 4 engines generate about 69,200 pounds of thrust to move the 336,500-pound aircraft. The nose lifts first, and finally, the massive wing produces enough lift for takeoff. At cruising altitude, the aircraft flies in extremely thin air. Flight control computers make thousands of adjustments per second to keep the tailless design stable. Approaching the target area, the crew begins the weapons checklist. They select a JDAM, and the rotary launcher rotates it into release position. The bay doors remain closed until the final moment to avoid radar exposure. When the doors open, airflow briefly shakes the aircraft, but computers compensate instantly. The JDAM awakens as the mission computer sends data through the umbilical. GPS coordinates, wind information, pressure data, time to impact, and attack angle. The bomb's internal computer processes everything in milliseconds while verifying every subsystem. Release occurs in fractions of a second. Hooks open, ejectors push the bomb clear, and it drops away at about 4 feet per second. The instant the umbilical disconnects, the thermal battery activates and the fuse begins its arming sequence. Tail fins deploy while the GPS receiver locks onto satellites. Inside the JDAM, the mission computer calculates its trajectory while considering wind, air density, and Earth's rotation. 2 seconds after release, the fins make the first adjustment to counter crosswind. The bomb does not truly fly. It falls with precision, trading altitude for lateral movement to guide itself toward the target. If GPS is jammed, the inertial system takes over with slightly reduced accuracy. As the bomb descends, corrections become smaller and more frequent. In the final seconds, the fins may adjust hundreds of times. The radar altimeter activates just before impact, and the last correction occurs a fraction of a second before the weapon strikes its target. This is World Watch, and that's what it really takes to put a single B-2 mission in the air. Precision, discipline, and thousands of perfect decisions working together. From silent preparation to pinpoint impact, every step matters. If you found this breakdown insightful, stay tuned for more deep dives like this. Until next time.